Today we're going to begin Chapter 3 in our algebra book. First, I'd like to talk about what a function is. This is something that you've already learned about in extended, and the definition applies also in traditional algebra. So, what is a function? A function is a correspondence between two sets where each element in the first set, called the domain, corresponds to exactly one element in the second set called the range. Remember, a function does not have more than one arrow going out. So here are two sets of ordered pairs, and this is how you tell if they're functions or not. In order to be a function, I cannot have the same x value going more than one place. So if I'm looking at a set of ordered pairs, I need to check to see if I have x listed more than once going to different locations. And in this case, I don't. However, in the second case, it's not a function because I have two values in the x component that are 1. I have 1 going to 1 and 1 going to 4, and therefore that is not a function. I can tell by looking at a graph whether or not something's a function by the vertical line test. If I look at the first graph, this is not a function. It's not a function because this x value is mapped to two different y values. It does not pass the vertical line test. Whereas this is a function. There's not any place on my graph that intersects this vertical line more than one place. Each x value goes to only one y. I can tell if a function is one-to-one based upon the horizontal line test. Remember, one-to-one means that there is no y value in the domain that has more than one arrow going in. So if I look at this graph, moving the picture. If I look at this graph, you can see that every y value is mapped to only once. So I do not have more than one y value for every x that is one-to-one. However, in this graph, it is not one-to-one. You can see that this x value goes to that y value. This x value goes to the same y value, and I have a third and a fourth place mapped to the same y value. So that is not one-to-one. I can further tell by looking at my order, if I look at ordered pairs. So this is how you tell if a graph is one-to-one. If a graph is one-to-one, it will pass the horizontal line test. If a graph is not one-to-one, it fails the horizontal line test, and that the horizontal line goes through more than one point on your graph. If I look at sets of ordered pairs, I can tell if a set is one-to-one by looking at the y values. If I don't have the same y value listed more than one time, then it is one-to-one. My top set is one-to-one, whereas my bottom set is a function because I don't have the same x value going more than one place, but it is not one-to-one because 1 is mapped to 2 and 3 is also mapped to 2. Now, if I want to look at a graph and tell if it's onto, I can tell by seeing if onto means I'm graphing everything onto the set in my domain. So or in my range, excuse me. So if I look at my y-axis, which represents all real numbers, it's onto if I can find a part of my part on my graph, an ordered pair on my graph that would contain every single y value along this y-axis. I think about it as if I'm taking my graph and I'm condensing it onto my y-axis. Every y value is mapped to. However, this graph is not onto. The y values above this point are included, whereas the y values below are not mapped to. So this is not one-to-one. Now I'd like to look at different types of functions and determine the domain. That is, possible values of x. So if I'm looking at a polynomial function, there are no x values that I need to exclude, which means the domain is all real numbers. For rational equations, meaning I have equations with variables in my denominator, I cannot have a value of 0 in the denominator. For radical equations with even index roots, I have to have the quantity under the radical greater than or equal to 0. It cannot be negative. Now, looking at this equation, it's a rational equation. I cannot have my denominator equal to 0. So to find the domain, I have to set the denominator not equal to 0. Once I do that, I can solve for those values that should be excluded. Once I do that, I know that my range is all real numbers where x is not equal to plus not equal to, it's hard to type this, I'm going to have to write it, plus or minus 5. So this is my domain, all real numbers where x is not equal to plus or minus 5. In my next example, I have a radical equation, and you'll notice that I have an even index root because that is the square root, which means this value underneath my radical has to be greater than or equal to 0. Once I set that up, I solve my inequality. So I subtract 9 from both sides, and then I divide both sides by -2. When I divide by a negative, I need to remember to flip the sign. When I write this in interval notation, it should look like this: minus infinity to 9, having a hard time with that one, 9 over 2. And I have to have a square bracket here because I want to include that 9/2. That is where my function will be defined. This is my domain from -infinity to 9/2. If I wanted to list the prior one in interval notation, it would be, let's see, it would be from -infinity to -5, and then union five with a curved parenthesis to infinity. Another curved parenthesis. Curved parentheses always go on infinity. So negative infinity is never included, neither is positive infinity. Now, if I have an odd index root, there's no restriction for what's underneath my radical, so my domain is all real numbers. The next thing I'd like to talk about are even and odd functions. Even functions are symmetric with respect to the y-axis. Odd functions are symmetric with respect to the origin. The algebraic relationship looks like this. F of -x equals f of x gives me an even function. F of -x equals negative f of x. That gives me an odd function. Now, I have 3 different functions that I'd like to look at, so I'm going to do an algebraic test. I put in -x for x, and then I simplify. Once I simplify, I notice that this function here is exactly the same as what I started with. Therefore, it's even. When I look at this function, again, I substitute in -x for x, And then I simplify. When I factor out a negative, I notice that that is equal to the negative of my function. That is odd. When I look at h of x, I substitute in negative x for x, and I simplify. I notice there's not any single way that this is equal to h of x, and it's not equal to negative h of x. So therefore, it is neither. Finally, increasing and decreasing functions. I just want to be able to state the intervals where my function's decreasing, where it's increasing, and where it's constant. So you can tell a function is decreasing when you look at your graph. You read left to right. If going left to right, you're going downhill, that's decreasing. If you're going uphill, it's increasing. If you go straight across, it's constant. So as I list where my function is increasing and decreasing, all of the values that I list are x values. So this function is increasing between -2, notice I am listing only the x values here. This one is increasing from -2 to -1, and then again from 2 to 4. It is decreasing from -infinity to -2, so over here, and then again from 0 to 2, and then again from 4 to infinity. And by the way, this should not be there. Then finally, it's constant as I look between -1 and 0. So again, we're only stating the x values, and we're looking for where we're going downhill, where we're going uphill, and where we're not going up or down, constant. Now I'd like you to look online and see your assignment and begin that. Have a great weekend.